What I want to do in this video is discuss what it means to be a metal or metallic nature. So first, let's just think about the metals that we encounter in everyday life, or based on our experience, the things that we associate with being a metal. So the elements that really jump out at us at metals, or we always refer to, hey, that's a metal or that's metallic, are things like iron, or nickel, or copper, or silver, or gold, or aluminum, or at least for me, these are the ones that immediately pop out. As hey, these are I've seen these things before, and they all feel like metals to me. But now let's think about what's true about these things, and as we'll see, many other elements on the periodic table that give them this metallic nature. What do we associate with having a metallic nature? Well, one is that these things can be shiny. These things tend to be shiny, that there's kind of a gloss when light shines on it. They're not just kind of a matte color. They look metallic, literally. That's sometimes the word that's used for it. It has a metallic shininess to it. Another thing that we associate with it is they tend to be fairly dense. If I take a metal, a block of a metal, and if I drop it into water, I imagine that sinking, that it's not floating on top of the water. We also imagine them having a very high melting point, that they tend to be solid at room temperature. Solid at room temperature. And as we'll see, this is true of all metals except for one of them, which is mercury, which is shiny, but at room temperature, as you might be familiar, is in its liquid form. Now, the other things that I associate with a metal is that I can make things out of them I can bend them and shape them in different ways. If I think of aluminum foil, I can bend it. It's not just going to crack. I can bend it and put it into different shapes. Even things like iron, it might take a lot of pressure to do it, but they're bendable, they're malleable. And definitely, things like gold and silver and copper, you can actually mold into different types of jewelry. If you put pressure on it, it's more likely to bend than crack and just kind of shear off. So let's put malleability. They're malleable. Malleable. And then the other thing that I associate with metals is that they conduct electricity well. Conduct electricity. A place that you'll see metal in your life is if you open up your electronics, you'll see wires that might be made out of copper, or you might have components that are made out of other metals like gold or silver or whatever else. So given that these are some of the properties that we associate with metals, let's think about what's happening at the atomic level to give these elements these properties. The way I think about it, let's just go with copper for a second. Let's just imagine a block of copper at the atomic level. So let's say this is one copper nucleus right over there, and it has its sea of electrons. It has its sea of electrons, just like, or not sea of electrons. It has all of its electrons in the various orbitals. We'll talk about sea of electrons in a second. But this is kind of its cloud of electrons, I should say. So this is electron cloud. So the electrons are just jumping around in this cloud. It's really a probability density, or there's kind of a certain probability that could be at any point in that cloud. And so let's imagine a big solid piece of copper. So you would have a bunch of these. You would have a bunch of these all together, all forming the solid. And what allows metals to be malleable, to do things like conduct electrons, or conduct electricity, which is the movement of electrons, is essentially for them, they're very willing to share electrons with each other. By sharing electrons, so you can imagine this is one copper atom, that's another. Let's say they're sharing some electrons. That's what allows the electricity, or this flow of electrons, to happen. If these electrons are loosely bound, then if you put a potential difference, a voltage, let's say that you put a potential difference so that this side is more negative and that this side is more positive, then the electrons are going to want to get away from the negative charge, move towards the positive charge. And if they're relatively freely bound, they can kind of move from one cloud to the next. And you kind of end up having what's often called a sea of electrons. Let me write that down. You have a sea of electrons, which would make this conductive. And that's why you see so much wire made out of copper. And the sea of electrons is also what makes it malleable. If someone on this side would have put a lot of pressure this way, and on that side put a lot of pressure that way, things that are rigid would just kind of crack and break right, would just break right over there. But because you have the sea of electrons, it allows it to be malleable. This part might just bend down a little bit. That part might bend up. But they're not going to, the metallic bond is not going to break. And so given that this metallic nature really comes from the willingness of these atoms to share electrons with each other, to create the sea of electrons, I encourage you to pause this video and think about which atoms on the periodic table, which elements are more likely to do that, to share electrons with others and with each other. And really this is the same principle that we thought about ionization energy and electronegativity. So pause the video. So I'm assuming you've had a go at it. So which elements are most likely to share electrons? Well, we've already seen that if we're on the left side of the periodic table of elements, group 1, for example, they only have one valence electron. It would be very hard for them to get enough electrons to complete that outer shell. And if they get rid of that one valence electron, they can go to a more stable state. So they really want to give away electrons. And the ones over here, they're so close. If we talk about the halogens, they're one electron away from completing their outer shell. They're greedy. They want to hog these electrons. They tend to be electronegative. The noble gases, they're done. They definitely don't want to share electrons with anyone. They're kind of in a very stable state. Now, the other thing that we've talked about is as we go down a group, our atoms are getting larger and larger and larger. So the outermost, that 55th electron in cesium, is much more loosely bound because it's further away than say the third electron in lithium. So just as we saw as the elements in this bottom left have a very low ionization energy. It doesn't take much energy to remove an electron from them. These are the ones that are most likely to share electrons, and these actually have the highest metallic nature. So high metallic nature. And the ones on the top right, these are going to be the opposite. They're very unlikely to share electrons. They're very electronegative. They have a very high ionization energy. They have a low metallic nature. So I can imagine some things are popping into your brain at this point. You know, we started thinking of the elements that in our everyday life we associate with metals. But what I'm saying is that these things over here have an even higher metallic nature. But what about something like calcium? You know, every day when when a lot of people imagine calcium, they think of kind of a white chalky substance, very rigid, not very malleable, not very good, not very shiny, not very good at conducting electricity. I mean, based on what I just told you, this would have a higher metallic nature than something like aluminum. What you have to remind yourself is that what you see is not actually pure calcium. That kind of chalky thing, that's calcium carbonate. Pure calcium, actually, this is actually a picture of pure calcium. And it is shiny. It does have these metallic properties. So the general trend here is that all of this is very high metallic nature, and these are very low metallic nature, which also makes you probably realize, wow, most of the periodic table is a metal of some form. If aluminum is a metal and all of these things have a higher metallic nature, then all of this stuff are metals. And that is the case. The S block, the D block, the F block, these are all metals. And then a good chunk of the P block, are considered metals, and then these are kind of sometimes referred to as metalloids. And then this section of the periodic table is not considered a metal, and that makes sense. The noble gases, they are gases. They are not very reactive. They don't bond, so they don't form kind of a structure that can even do this type of thing. And these other ones over here, even carbon, when it formed a lattice, it does not conduct electricity well. It's not so. It tends to not be so malleable. If you think about something like a diamond, or if you think about, well, a diamond might be the best example of that. So anyway, hopefully this gives you a sense of metallic nature and the trends in the periodic table. High metallic nature, and as you go to the top right, lower and lower metallic nature.